Assalamualaikum and a very good day to my respected lecturers and my fellow classmates. My name is Radin Atika binti Abdurrahman and today I will be presenting about a research article entitled Circular RNA Vaccine with Long-Term Lymph Node Targeting Delivery Stability After Lyophilization Induce Potent and Persistent Immune Response by one published in 2024. Imagine a vaccine that is not only more effective but also easier to store and transport. This is exactly what researchers aim to achieve through the development of a novel circular RNA vaccine platform. In this presentation, I will discuss the research background, problem segment, methodology, key finding and also the significance of this biotechnology innovation. Without further ado, let's begin. To begin, let's look at the background of this research. mRNA vaccine became widely known since the COVID-19 pandemic and demonstrate remarkable effectiveness against infectious disease. However, despite their success, they still have several important limitations. First, mRNA molecules are fragile and can degrade easily. Second, immune protection may decrease over time, requiring booster vaccination. Third, many mRNA vaccines require strict cold chain storage, making transportation costly and challenging, especially in the remote areas. So, to address this problem, researchers explore circular RNA, unlike conventional mRNA, form a closed circular structure, making it naturally more stable and resistant to degradation. At the same time, researchers recognize that directing vaccine to lymph node could improve immune response because lymph nodes are where many immune cells become activated. By combining this idea, it led to the development of this innovative vaccine platform. So what problem were the researchers trying to solve? Current vaccine technology often struggle to achieve three important goals simultaneously. First, long-term stability. Secondly, efficient delivery. And thirdly, durable immunity. So in addition, while freeze drying has been used to improve vaccine storage, its effect on lymph node target vaccine delivery had not been fully investigated. So therefore, the researchers aim to develop a vaccine that could remain stable during storage, efficiently reach lymph node, and produce long-lasting immune protection. In simple terms, they want a vaccine that works better, lasts longer, and is easier to distribute. To achieve this goal, the researchers first developed a rabies vaccine based on circular RNA. Next, they encapsulated the circular RNA inside manus-modified lipid nanoparticle, or known as mLNPs. The manus molecule on the surface help guide the vaccine toward dendritic cell and the lymph node where the immune response begins. The researchers then evaluate several aspects of vaccine performance. They examine whether vaccine successfully target lymph nodes, whether it stimulates antibody production, whether it generated immune memory, whether it protected animals from rabies infection, and lastly, whether it remains stable after freeze drying. Using this experiment, they could determine whether the new vaccine platform offers advantage over conventional approach. The first major result is shown in the first figure. The researchers found that the manus-modified nanoparticle accumulate more efficiently in lymph nodes compared with conventional nanoparticle. Why is this important? Because lymph node act as training center for the immune system. The more vaccine that reach this site, the better the immune cell can recognize and respond to the antigen. The study also shows significantly higher neutralizing antibody level in vaccinated mice. Neutralizing antibody are one of the most important indicators of vaccine effectiveness because they can directly prevent virus from infecting cells. This finding demonstrates that targeted delivery successfully enhance the immune response and improve vaccine performance. The next question is whether this stronger immune response actually translated into protection. The answer is yes. As shown in this figure E, mice vaccinated with the MLNP circle RNA vaccine achieved 100% survival after exposure to rabies virus. This is a remarkable result because it demonstrates that the vaccine provides strong and long-lasting protection against infection. The researchers also investigated storage stability. After the vaccine was freeze-dried and stored at 4 degrees Celsius for 24 weeks, it still maintained high neutralization antibody level. This means that the vaccine remained effective even after long-term storage. Together, these findings suggest that the vaccine is not only highly protective but also much easier to store and transport. So now, let's discuss why this vaccine performed so well. The first reason is the use of circular RNA technology. Because circular RNA form a closed-loop structure, is more stable than conventional mRNA and can continue producing antigen for a longer period. This results in prolonged immune stimulation. The second reason is the BMS modified lipid nanoparticle. This nanoparticle specifically target dendritic cell and lymph nodes, allowing the vaccine to reach the most important immune tissue more efficiently. The third reason is lyophilization or freeze drying. This process preserves the vaccine structure and maintain its effectiveness during the storage, helping overcome one of the biggest challenges faced by RNA vaccine today. Overall, this study successfully combined RNA biotechnology, nanotechnology, and pharmaceutical engineering into a single innovative vaccine platform. To conclude, this study developed a novel lymph node targeted circle RNA vaccine using BMS modified lipid nanoparticle. The vaccine successfully enhanced lymph node targeting, generates strong neutralizing antibody response, provide complete protection against rabies infection in mice, and maintain stability after freeze drying and long-term storage. These findings suggest this technology could represent the next generation of RNA vaccine, offering improved effectiveness, durability, and accessibility. Thank you for your attention. That's all from me. Thank you.